Hello everyone, welcome to the channel of Algocamp. So in this particular series, we are going to start talking about a few interesting concepts around data structures and algorithms. These videos are going to be power packed with in-depth explanations, problem solving around some very important aspects of data structures and algorithms. DSA is one of the most important topics when you see software engineering interviews for both internships roles and full-time roles. And I see that a lot of people actually struggle with that. So in this particular video series, what I have tried is I have tried to make sure that I try to solve the problems and try to explain the corresponding concepts with a more intuition building kind of like a scene. And we will be doing a lot of pattern based problem solving so that you can actually see what kind of problems can be solved with a specific type of algorithmic pattern. In this particular start of the series, we are going to actually start with searching algorithms. I believe searching algorithms are one of the most important algorithms if you want to actually excel in DSA, and a lot of advanced concepts in DSA do rely on searching algorithms. So without any further ado, let's just start this particular video, but I would highly encourage you to do subscribe to the channel if you have not yet subscribed, because we are going to put some really awesome content coming up ahead, and all of these videos are going to be really helpful for you for preparing for your next software engineering interviews. So let's just start. So this is a new problem coming in front of us. The problem is from interview bit. The problem name is Painter's partition problem. The problem has been previously asked in multiple companies like Google, Codenation, Amazon, right? The problem says that given two integers a and b, so you'll be having an integer a and you'll be having an integer b, and an array of integers c. So you'll be having an integer array and two separate integers a and b. This integer array is of size n, right? Element ci represents the length of the ith board. So every element of the array is actually going to represent some board to you. Okay, so it's actually representing length of the ith board. So most probably there is going to be n boards, n different boards, and you are given the length of every ith board. You have to paint all n boards. You are expected to paint every single n board, that is from the 0th index to the n minus 1th index. There are a painters available. So total number of painters that you have got with yourself are a. There are a painters available, and each one of them takes b unit of time to paint 1 unit of board. So you have total a painters, and every painter takes b unit of time to paint 1 unit of board. For example, if the value of b is 3, then every painter, right, all the a painters, let's say you have 10 painters, every painter is going to take 3 unit of time to paint 1 unit of board. Okay, you have to calculate and return the minimum time required to paint all boards under the constraint that any painter will only paint contiguous sections of board. So what you have been given here is that every painter is expected to only paint contiguous sections of board. It's not like you can paint the first board and then you can paint the 10th board. No, you have to paint only contiguous cross sections of board. So if you have picked 1, then you can pick 2, then you can pick 3, but you cannot pick 5 if you have not picked 4, right? So you have to calculate that given the fact that you have a painters, then what is the minimum possible time in which you can paint all of the boards, all of the n boards, such that every painter is going to take b unit of time to complete 1 unit of board. You have to calculate minimum time required. A note here is given that two painters cannot share a board to paint. So if one board has been allocated to a painter, only that painter can paint that board. That is to say, a board cannot be painted partially by one painter and partially by another. So you cannot do like half unit of the board has been painted by someone else and the rest half is painted by someone else. A painter will only paint contiguous boards. This means a configuration where painter 1 paints board 1 and 3, but not 2 is invalid. That means it's not like you can paint the first board and directly the third board and you're not painting the second board. This configuration is not possible. If you want to paint the third board and the first board, then you are bound to paint the second board also, so that contiguity is maintained. Whatever is your final answer, you have to just return that modulo 10 raised to the power, I guess, This is 1, 2, 3, 4, 5, 6, 7. 10 is per 7 plus 3. So this value modulus you have to actually return. The length of the array A can be 10 is per 3. The value B can be 10 is per 6. N can be 10 is per 5. And every individual, sorry, N is the length of the array. So length of the array can be 10 is per 5. Every individual board height can be 10 is per 6. Total number of painters that you can have is 1000. And for painting 1 unit of time, the time taken by each painter can be as big as 10 raised to the power 6. So let's say you have two boards. One board is of size 1, one board is of size 10. There are two painters. Each painter take 5 unit of time to paint one single board. Now in this case, because you have two boards, the output is going to be 1. Let's see how. One possibility is that one painter paints both the blocks. So if you have two painters, it's not necessary that you deploy both the painters. Let's say you allocate the task to only one painter. Then there are total what? 11 units of board to be painted. 1 unit of board will be painted in 5 minutes or 5 units. So 11 units will be in 55 units. Whereas the possibility 2 is that painter 1 paints block 1 and painter 2 paints block 2. So because they are going to start painting parallelly, in 5 units of time, painter 1 will be done with its task and painter 2 would have done 1 unit of task. Then after 9 more units of task, painter 2 will complete this. So the time taken is going to be 50 units. Can I say that? Because now this board gets parallelly allocated to someone else. So 50 is the answer. 50 mod 10 is per this is 50 only. Whereas if let's say you have these many boards, you have 10 painters, every painter can paint in 1 unit of time. Then in that case, what you can do, you can deploy 4 painters. Every painter will paint individually. And the longest time taken by any painter is going to be 11 units. So in 11 unit of time, all the boards will be painted. That's what you can even see here, right? So this is the problem statement in front of us. I hope the basic problem statement and the crux of the problem statement is clear to everyone. Now, how can we solve this particular question? So I have a basic test case in front of us, right? So a few things that you have to keep in your mind is that we have to calculate minimum time. Okay. So generally what I do when I approach a problem is that I see that what kind of a situation we have. Whenever you have to calculate something around minimum or maximum, these kind of stuffs when we have to do, then generally some approach around binary search or something around brute force generally helps. Okay. It's not a counting problem, right? It's a minimum calculation or a maximum calculation kind of a problem. So generally we can at least think in directions of binary search, that can I apply binary search here? It's like maths. In maths, when you have a numerical, then you don't know the exact solution, right? Then you try to think it in terms of formula, that you try to break your given equation into some other equation. Maybe that can help you to derive an answer, right? So similar thing we do here. I say that whenever you have something like minimization of a value over a maximization of value, some minimum calculation or maximum calculation is there. One approach that you can move forward is definitely binary search, right? Okay. Now, what we can say here is that the other condition is painters need to manage continuous cross sections, right? We have to always manage continuous cross section. That is, if one painter has started to paint something, they cannot go beyond this. Okay, they cannot go beyond that. They have to keep continuous cross section always. For example, let's say if we have fences or boards to paint, then let's say the first painter paints the 3, then the second painter paints the other 2. It's not like the first painter painted this, first painter painted this, first painter painted this. It's not gonna happen like this. There cannot be loss of continuity. Okay, cool. Third one. If a painter is allocated a board They are bound to complete it. They are bound to complete it. Okay. So we have these three observations. Apart from that, now whenever I try to solve the problem, I try to also see the constraints. Like based on the constraints, I can see that the length of the array is as big as 10 raised to the power 5. It's quite high, right? Like n square based solution won't be submitted. I don't need to think in terms of something like n square because n square won't help a lot, right? So now what we can do? I'm saying that because it's a minimization or a maximization kind of a problem, binary search might be a good idea to go for. So if you have to try to apply binary search here, the first principle of applying a searching algorithm is to define the search space. Okay. Now, what is the answer that we have to calculate? The answer that we have to calculate is minimum time. And this array is of what? Board length. So of course, this array is not my search space. This array is not my search space. My answer is minimum time. So my search space should be somewhere around minimum time only. If let's say this would have been a question of searching inside an array, then my search space would have been an array. Now this array is of board length. It's a board length array. I have to calculate minimum time. So this might not be the best search space that we need to look for. We need to look for a search space that quantifies for time. Now we don't have an array. But what we can do is, we can try to define a range between which our answer might lie. We can define a range of number between which our answer might lie. And then on that range of number, if we are able to successfully define a search space such that we divide the search space into two parts and one half is different than the other half, then maybe binary search can be applied. Now you tell me, we have to calculate minimum time, right? Minimum time taken. In the best case, what will be the minimum possible time? Minimum possible time in worst, like the best case possible. Can I say the minimum possible time will be what? If let's say the array is of length n, right? And arrays of length n, and we get n painters, approximately we get n painters, right? And we parallelly deploy every painter. We are never going to allocate two boards to a painter. We are parallelly deploying every painter everywhere, right? This will be the case where the time consumed will be the minimum, right? This will be the case where the time consumed will be minimum. Although we don't have 5 painters here, but the best case would have been that we have 5 painters. It's a 5 length array. Every painter paints parallelly. Then the minimum possible time taken would have been minimum element of array. Can I say that? Minimum element of array multiplied by b. Because 1 unit of board is going to be painted in b unit of time, right? So if you see P1, P2, P3, P4, P5, if we have 5 painters deployed, P3 is going to take the most amount of time. And how much? It's going to be 30 into 1, that is 30 units of time. The other 4 are going to parallelly complete till the time P3 completes. So this is going to be the minimum possible time that in any case you are going to take, no matter what. You cannot do anything better than this. We cannot do anything better than this. Right? We cannot do anything better than this. Okay, cool. That being said, what will be the worst possible situation? Worst case. That is maximum possible time. Maximum possible time will be when you have only one painter and that painter only has to paint all of the boards. Can I say that? The minimum time was when we have one painter for each board. This will be when we only have one painter. This will take the maximum time. Why? Because this one painter only has to paint first, second, third, fourth, fifth, all of the boards. So what will be the maximum possible time? The maximum possible time will be summation of, this is array C, right? C of I starts from 0 to n minus 1 multiplied by B. Why? Because the total units of board that are expected to be painted is what? Sum of these board length, and in 1 unit, to paint 1 unit of board you need B unit of time. So to paint all of these boards you need sum of all of them multiplied by B unit of time. This is the maximum possible time that you can get. This is the maximum possible time that you can get. Can I say that? So these are the typical bounds that you can think of, right? Now, because you are new to problem solving, in this problem I helped to think about the best possible case and the worst possible case. But when you are new to problem solving, what happens is you are generally not able to think about the best case and the worst case. So if you are not able to derive an exact equation, what you can say that what will be the minimum possible time? In our case, minimum element of the array can be of length 1, minimum value of B can be of length 1, so 1 into 1 will be 1. So approximately I can say in the best possible case, in 1 unit of time you will be able to do everything. And maximum will be what? The maximum value is like sum of the array. If the maximum value of the array is 10 raised power 6, sum of all of them will be approximately around 10 raised power 6 or 10 raised power 7 only. Multiplied by B, maximum value of B, if you see, maximum value of B is also 10 raised power 6. So 10 raised power 6 into 10 raised power 6 will be what? Approximately 10 raised power 12. For safety, you can take 10 raised power, let's say 14. That this will be max to 10 raised power 14. It can never go beyond 10 raised power 14. So instead of actually calculating the exact values, you can take loose bounds, or you can take approximate values, that from 1 to 10 raised power 12 or 1 to 10 raised power 14. It's a good range to go for, right? Because the time taken will never be less than 1 unit of time. Okay. But for the timing, we can see that this is the best case, this is the worst case, and maybe we can move forward with that. So what I can say is that if you know the best case and if you know the worst case, now we have defined our search space, right? We have defined our search space. Can we apply binary search on this search space? Let's see. If we are able to divide this search space into two halves, and we are able to figure out whether one half is different than the other, then we can say that we will be able to apply binary search. Okay, let's cut this test case, copy, paste. Now what will be the best case value here? Best case value will be minimum value is 5 into 1, that is 5. Worst case value will be what? Sum of all of them. So 30 plus 20, 50, 60, 75, 80. Right? 80 into B. 80 into B. So this will be the maximum unit of time that you can take. Okay. So whatever is your answer is going to lie from 5 to 80. Okay. Whatever is your answer is going to lie from 5 to 80. You cannot do anything in less than 5 unit of time, and you never need anything more than 80 unit of time in this particular test case. Can I say that? Okay, because this is 5 into 1, this is 80 into 1. Now let's calculate a mid. 80 plus 5 by 2, 85 by 2. 2 4s are 8, 2 2s are 4, approximately 42 something, right? So we can say that mid value is 42. Okay, mid value is 42. Now we have to check that are we able to paint all of these boards using 3 painters in 42 unit of time or not. We have to check. Are we able to paint all boards in mid unit of time? Okay, cool. Now just think about it. We have to just figure out whether we can paint all of the boards in mid unit of time. That is, can we paint all of the boards in 42 unit of time? Just think about it. If we are able to print everything in 42 unit of time, then we will be able to print all of them in more than 42 unit of time also, right? If we can paint all boards in mid unit of time, we can definitely paint them in more than mid. And we want minimum answer in which you can paint all of the boards, right? So now we know that if we are able to paint all of the boards in 42 unit of time, we will be definitely be able to paint all of them in more than 42 unit of time. And I want the minimum possible time, right? So 42 can be a potential answer. This can be a potential answer, right? But we may find anything better than this on the left side. We might find something lesser than 42, that is even lesser time on the left side of 42. So what we are going to do, discard right. Discard right. How do you discard right? You do high is equals to mid minus 1. Okay. And just think about the opposite way. If we are not able to print, or I would say if we are not able to paint in 42 unit of time, that is mid unit of time, I cannot paint it in less than mid unit of time, right? If 42 cannot become my answer, anything less than 42 can also never become your answer. But we are not sure about the right half. On the right half, you might have some values which are not your answer, not possible answer. You might have some values which are your possible answers. Can I say that? So let me write this also. If we are not able to print or paint in mid unit of time, then we can't paint in less than mid. So everything less than mid is a waste for us. You say discard left. Okay, you say discard left. So that's going to be our agenda, right? That's going to be our agenda. That if we are able to do something in a particular unit of time, you will try to find something better than that. If you cannot do something in mid unit of time, you won't be able to do it in less than mid unit of time. So you find something more than mid. That's it. We are able to somehow apply binary search here, right? The only piece of the puzzle left is that with a given value of mid, how can you check whether you can paint everything using A painters or not? Using A painters or not? This is the only piece of puzzle left. Once we are able to decipher it, the whole problem is going to be solved. So how can we solve this piece of the puzzle, that once we are given a mid value, let's say 42, how do we know whether we can paint everything in 42 unit of time or not? How to know if we can paint everything in 42 unit of time, or in general sense mid unit of time? How do you know that? We will be able to paint all of the boards in mid unit of time if and only if every painter takes maximum mid unit of time and all of the boards get consumed. If every painter takes max mid unit of time and consume painting of all boards. Right. So let's see. Now we have three painters, right? A is equals to 3. So we have three painters, P1, P2, P3. Can P1, P2, P3 paint all of them in 42 unit of time? Let's try to see that. Okay. We start with painter 1. The maximum limit for a painter is 42. One painter can be allocated 42 units of time or 42 unit worth of board. Okay. So if painter 1 starts with the 0th board. Okay. To paint the 0th board, it takes 5 into 1. 5 unit of time. Your limit is 42. Painter 2 can be expanded to 1 also. This becomes 10 plus 5, 15. 15 into 1 is 15. 15 is also less than 42. No problem. Let's move forward. 30. 30 plus 15 is 45. 45 into 1 is 45. Is 45 less than or equal to 42? No. That means painter 1 cannot be allocated all three boards. All three starting boards cannot be allocated to painter 1. So the best our painter 1 was able to do was only the first two boards. Painter 1 cannot be given anything more than two boards. That means we need to deploy another painter, painter 2. We need to deploy one more painter, right? So now painter 2 starts with 30 unit board. To paint a 30 unit board in 1 unit time per unit board is 13 to 1. 32 into 1 is less than 42. We are good to go. We'll try to include the next board also. 30 plus 20 is 50. 50 into 1 is 50. Is 50 less than 42? No. That means painter 2 cannot be given anything apart from this single board. Painter 2's whole time is going to go inside this single board only. Okay. Then we'll start with painter 3. Okay. Painter 3 says, I'm going to take 20 unit. So 20 into 1 is 20 less than 42. 20 plus 15 is 35. 20 plus 15 is 35. And if you carefully see, if I include both of them, then painter 3 can complete this painting in less than 42 minutes, right? You have been given 42 units. When I say minutes, then I'm actually meaning the units only, right? So we can say that painter 3 can cover everything in less than 42 minutes. So if you allocate the boards such that first two boards goes to painter 1, second board goes to painter 2, next two board goes to painter 3, then in 42 unit of time, I can paint all of the boards. If I can paint all of the boards in 42 unit of time, I can paint all of the boards in more than 42 units of time also. And we want to find a better answer. So we have found one potential answer. One potential answer is 42. And I will try to find something better than this. So I'm going to discard my right half. And I'm going to bring high here, which is 41. Right? And we will reset the situation. We will reset the situation. So if you carefully see, in order to check whether a particular mid value gives a potential answer or not, you iterated on the whole array, right? 5, 10, then 30, then 20, 15. So you read the whole array, then only you were able to decide whether mid is a possible answer or not. Okay, let's try again. Now high is at 41. We calculate mid. 41 plus 5, 46 by 2, 23. Now the question is, can we paint all of the boards with 3 painters with b is equals to 1 in 23 unit of time? Let's see. Let's see. We start with painter 1. We start with painter 1. Okay. Painter 1's starting board is of 5 unit. Okay. So 5 into 1, 5. Is it less than 23? Yes. So painter 1 can be allocated this board. Then if you expand for painter 1, then this is 15. 15 into 1 is less than 23. Painter 1 can be given these two boards. If you try to expand for painter 1, this is 45. 45 into 1 is not less than 23. So you cannot allocate this board to painter 1. You need to deploy the next painter, painter 2. Okay. Now there is a problem. 30. Right. If you carefully see, 30 is more than 23, right? And we actually made a small mistake here also. So technically, the best case won't be minimum element. This should be maximum element, right? This should be maximum element. Maximum element of the array. For example, every painter gets deployed parallelly. Then in 30 units of time, you will be able to complete everything, right? So it's maximum element of the array into B, not minimum. So technically, your search space should never consider 23, right? Your search space should be always somewhere around 30. But as I said, it's not always necessary to keep exact bounds. You can take loose bounds also. So even you took 5, nothing is going to hamper. But here we can directly see that this 30 is greater than 23. We cannot paint all of the boards in 23 unit of time. We need to move forward with 24 as low. Low comes here. Okay. Low comes on 24. Right. Cool. As I said, like you don't need to always formulate this value. Eventually, when you will actually try with loose bounds, they will automatically correct themselves, right? They will automatically correct themselves. Okay. Now, high is at 41, low is at 24, mid calculation, 41 plus 24, 65. 65 by 2, 2 3s are 6, 32.5, so approximately we'll take 32. Okay. Mid comes as 32. Can we paint in 32 unit of time? Let's see. Painter 1 will be given these two. Painter 2 can be given this. Can we allocate this to painter 3? Yes. 20 into 1 is less than 32. Can we allocate both of these to painter 3? 20 plus 15 is 35. 35 into 1 is 32, is not less than 32. This case is also not possible. We cannot allocate everything. So this possibility is not going to work. We will say low is equals to mid plus 1. We need to increase the time. Okay. So low technically comes at 33. Right. So let me refresh the search space. So low comes as 33 and high I guess was at 41. Okay. We'll calculate mid again. So 41 plus 33 is what? 74. 74 by 2. 2 3s are 6. 2 7s are 14. 37. Okay. Can we paint in 37? Yes, you will be able to paint. Allocate this to painter 1, painter 2, painter 3. 37 is possible. If 37 is possible, I have found a better answer. I need to find something even less than 37. High comes as 36. We calculate mid again. 36 plus 33. 69 by 2. 2 3s are 6. 2 4s are 8. 34. Can we paint in 34? We won't be able to paint in 34. This to painter 1, this to painter 2. But painter 3 can only paint this one. It cannot be allocated the last one. So 34 is not possible. We do low is equals to mid plus 1. Low comes as 35. So low at 35, high at 36. 35, 36, 6, 5, 11, 7, 71. 71 by 2, approximately 35. So mid comes as 35. Can we paint in 35? Yes, you will be able to paint in 35. These two to painter 1, painter 2, painter 3. 35 is a better answer. You will update your answer to 35. And then move to high is equals to mid minus 1. So high goes to 34. And you can see now high is at 34, low is at 35. Your search space ends. Your answer is 35 and 35 is the answer for this test case also. So all you have to do is keep on allocating. Start with the first painter. Keep on allocating the current painting or the current board to the current painter. Next board to the current painter till the time total time into B is less than your mid, less than or equal to mid. The moment it shoots up more than the mid, you have to allocate this to the next painter, right? And if you are able to somehow simulate this, then for every mid value, then for every possible mid value, you have to iterate on the whole array. Can I say that? The array length is n. That means for every iteration of binary search, you do order of n task. For every iteration of binary search, you do order of n task. How many iterations of binary search will be there? It will be summation minus maximum element. So approximately you can say summation of all of the elements into B, right? So if you carefully see, then time complexity will be what? Order of n into log of summation of Ci into B. Can I say that? If you see, summation of all of the elements is going to be approximately 10 raised per 6. B is going to be approximately 10 raised per 6. So log of 10 raised per 6 into 10 raised per 6 is what? Log of 10 raised per 12. What is log of 10 raised per 12? Approximately 40. 40 into n. N is 10 raised per 5. Will be approximately 10 raised per 5 only. This solution will get submitted. So n into log of summation of elements into B. That's also technically a very loose bound. This should be summation of elements minus maximum element into B. Right, but I am considering that this will be approximately 1. This will be approximately 10 raised per 12. So this solution will work in n log of summation of all elements into B time. And this is definitely a workable solution. And we are able to come to this solution using binary search. And there was no array on which we applied binary search. technically we applied binary search on the answer. What was the answer? The time value. And I just showed you, right? Worst case, we took exactly same. Best case, we took less than the technical bound. The technical bound was maximum into B. We took something even less than that. Still, binary search was able to converge it. So when you are in an interview or you are in a competitive programming test or anywhere, you don't have to waste your time by thinking about exactly same bounds. If you're not able to think about it, you can take some approximate value that can be even less than the possible minimum value or more than the highest possible value. Still, binary search will be able to manage everything. But of course, if you are able to think about exact bounds, it's a good to go. We just did one small mistake. We should have taken maximum because this will be the minimum time that anyone is going to take. And this is how you can implement the painter partition problem. If I just give you a quick pseudocode, right, on how to actually implement this, then I can write a function can paint boards. Okay, this function is going to tell that whether my A painters can paint all of the given C boards or all of the given N boards inside the C array, right, in mid unit of time, such that every painter takes B unit of time to paint 1 unit of board. Okay, this will be my can paint board function. See, A is the number of painters, C is the board length array, N is the total number of boards, mid is the maximum time one painter can take, and B is the per I would say how much time you are going to take for painting per unit of board. Okay, cool. Now we'll say answer is equals to 1. Can I say at least I will require one painter, right? So let's not even say it as answer. I will say painters is equals to 1. I'm going to at least start with the first painter, right? At least one painter will be required. At least one painter. Can I say that? Okay. If at least one painter is required, then we can start doing the painting. Okay, we can start doing the painting. We will say while, and I will say board let me say units painted is equals to 0. Initially, the first painter has not painted anything, right? So we can say units painted is equals to 0. Let me write it cleanly. Units painted is equals to 0. Then we can say while units painted, and I can take a variable I also, I equals to 0, right? Or let's put a for loop maybe. For I equals to 0, I less than n, I plus plus. Okay, we'll go to every board one by one. We will say if units painted plus C of I into B, that is the previous set of units you have painted up till now, plus the new board that is going to be allocated. If the time taken for overall of that is greater than mid, right? So see what I'm saying. Whatever time you have taken in order to paint the previous units of board plus the new time that will be taken if I allocate you the ith board also. If this total time is greater than mid, then I need to allocate this particular board to a new painter. So I will say painter plus plus. Painter plus plus. Why painter plus plus? Because I cannot allocate the ith board to the current painter. Because if I allocate the ith board to the current painter, the time limit will be exceeded. The time limit is just mid. So that means I need to allocate this to the new painter. Can I say that? I need to allocate this to the new painter. And I need to also do units painted is equals to 0. Okay. And I will not do I plus plus here. I'll do I plus plus separately. Okay. So now I am starting with another painter and I'm going to reset the painting count because a new painter has been allocated, and I will do continue. I will do continue. Okay, I will do continue. So see what is happening. If the current painter cannot paint the ith board, you will start allocation to a new painter, reset the painted count and continue. Continue means you are again going to check whether the current painter can be painted by the new painter. This is 0 plus this value. If this value is greater than mid, then you won't be able to do it. You will allocate this to another painter and so on. You can keep on allocating like this, right? And if that is not the case, if this if check is not the case, else what will you do? That means the current painter can paint the painting, right? So you will say units painted plus equals to Ci into B. So the same painter is going to paint these many units also. And then I'll do I plus plus. That's why I was initially writing a while loop. So now I'm saying that this painter can paint the ith board, no problem. Allocate this to him or her, whatever it is. And the total units that they have painted is going to be added with the new unit of time for the current board. And now I'm going to move to the next board. Right, I'm going to move to the next board. What will be my final value? My final value will be return painters is less than or equal to A. That is, if to paint the total number of boards, if the painters required are less than or equal to A, then only we were able to paint everything in B, everything in mid unit of time. Otherwise, we required more painters, right? Otherwise, we required more painters. Or what you can do, you can put this check here also. You can put this check here also. Just here. When you do painter plus plus, right? Before allocating to a painter, you can say that if the painter count become greater than A, return false, because technically now you won't be able to paint it, right? Now you won't be able to paint it, right? So anything you can do, you can keep a painter count here, then you can just directly return a true here, because if you are able to paint everything, you just return a true. So using this simple logic, and what is the time complexity? See, for loop, if else, nothing else, order of n, right? This function is going to work in order of n. So in order of n, you will be able to check whether in mid unit of time using A painters with B unit of time per unit of board and total n boards, can you paint all the boards? This will be a simple for loop that you can actually write here. And the other part is going to be just your binary search. You will say low is equals to max into B, high is equals to, somehow you will get sum of the array into B. You will say while low less than or equal to high, you will calculate mid, low plus high minus low by 2. You will say that if can paint, right, can paint boards, and you will pass, let's say, ACN mid B. If they can paint the board, I will say answer is equals to mid, and I will try to find something better. So I is equals to mid minus 1, else low is equals to mid plus 1. That's it, right? That's it. This is going to be the final implementation. This is going to be the part of binary search, and this is going to be the part of can paint boards. You can just implement this solution directly and you will be able to get your final implementation. Let's try to code this solution and see if we are on the right track or not. So first of all, I'm going to write a function. We can do it here. Can paint boards. Okay. To comma, and you can even write it outside. If you don't understand module.exports and everything, don't worry. Later when you learn Node, you will understand it. Okay. This can paint board is going to take A, the array C, length of the array, mid, and B. Okay, cool. What we're going to say, we'll start with the first painter. Units painted is equals to 0. We say let I equals to 0. We'll do a while loop I less than n. We will say if units painted plus C of I into B is greater than mid, that means we need to allocate to a new painter. Painters plus plus, and this is painters. If painters count become greater than A, you return false, because now you need more painters and you don't have that many painters. Otherwise, you say units painted is equals to 0 and you do continue. Else, you will say units painted plus is equals to C of I into B, I plus plus. At last, you return true. If you never did anything, you return true, or technically, just to be more safe, you can say the painters that were required were less than or equal to A, then technically it is going to be true, right? Because if let's say you are on the last painter, then also this condition will be automatically handled. Okay. Now let's try with the binary search. We'll say let low is equals to, let's track the max and the sum of the array. So we'll say let max element is equals to -1. Let summation is equals to 0. For let I equals to 0, I less than C dot length, I plus plus. We'll iterate over the array and we'll calculate the maximum element, the summation, right? So we'll say summation plus equals to C of I, that is sum of the array, and max element is equals to math dot max of max element comma C of I. Then we'll say let low is equals to max element is into B, let high is equals to summation into B, while low is less than or equal to high, we say let mid is equals to low plus math dot floor of high minus low by 2, and we say if we can paint board A, C, N, mid, B, then we say answer is equals to mid, high is equals to mid minus 1. That is, you try to find something even less than the current mid, or low is equals to mid plus 1. Okay, let's initialize an answer variable. At last, we do return answer. Okay, let's try to test the code and see if it is working fine or not. So before you submit, the answer expects you to do answer mod this. Now, because we are coding in JavaScript, the bounds of integer are quite high, so it is going to handle everything. You don't need to apply modulo arithmetic, right? And you just do answer mod this value and try to submit. It's going to submit the whole problem, no problem in that, right? Otherwise, there is a concept of modular arithmetic that we can talk about later, that sometimes you might have to apply, but because you're coding, this coding implementation is in JavaScript, so everything will be handled. If it would have been C++, then a bit of work we might have to do due to this modular arithmetic, but you can see the overall coding implementation is working absolutely fine. So now for this particular solution, what will be the time complexity? If you just carefully see, here we are having a while loop. You can replace it with a for loop also, which is just iterating over all of the elements of the array one by one, right? So this is a order of n loop, and this is the binary search in which we are again and again calling this function which is having an order of n loop. This binary search is going to work in log of summation into b minus max into b time. So log into n is going to be n log of summation into b minus max element into b, that we have also deciphered here, right? So in the coding implementation also, you can see this is the final answer, right? One small piece of thing, if you have to just quickly check to calculate the maximum element and the summation, what I did was, before actually starting binary search, I applied a loop on the whole array, added every element in the summation variable, and did math.max of maximum element comma the current variable. So initially it is -1, right? All of the array elements are going to be expected to be positive because the length of the board will be always greater than 0, right? So if you start with -1, this is the minimum possible value. And then whatever is the next value, it will be always either greater than that, right? Initially. So you start with comparing -1 and some value, which will be greater. This value will be greater. And then again and again in the loop, you will check what was the last greater value and what is the current value, which one of them is the greatest. And then you assign it back to max element. This is a simple maximum check that you can apply. Also, if you are somebody who is actually willing to prepare for software engineering interviews and want a more structured curriculum around high-level design, low-level design, other aspects of interview preparation around system design, or you are more interested in around learning back-end development concepts with Node.js, Spring Boot and whatnot, then do check out the website of algocamp.io. Here we have tons and tons of live courses where we talk about some really interesting concepts around software engineering. So do check out the website and start preparing for your software engineering career, because all of the concepts that we are going to talk about are one of the most important ones to become a better engineer and also to actually crack all the software engineering interviews. So let's come back to the video. So this is a new problem in front of us. The problem says that you will be given a list of numbers from 1 to n. Okay. Each number is considered as one stick. Okay. The ith stick will be having a specific length. So every stick will be having some specific length. We need to play a game in this problem. We need to pick 3 sticks randomly, and if our opponent is able to form a triangle using those 3 sticks, he will win. Okay. So we need to find any 3 random sticks. Okay. And if the opponent in the game is able to form a triangle with the 3 sticks that we randomly picked, then they will win. Okay. Our task is to find the number of ways to select 3 sticks such that it is not possible for our opponent to form a triangle using them. So we'll be having a set of sticks where we will be given the length of each stick. We need to find that in how many ways you can pick the 3 sticks such that you cannot form a triangle out of it. Okay. Let's see how can we solve this problem. If you carefully see this test case of 4 to 10, then there is one way in which if we pick the sticks, we won't be able to form a triangle. That is this given way only. Using these 3 sticks, if you are only having 3 sticks and these are the given 3 sticks, you won't be able to ever form a triangle, right? Okay. Whereas if you have an array like 5, 2, 9, 6, okay, let's say you have this array, and now in this array you have to figure out in how many ways I can pick the 3 sticks such that we cannot form a triangle out of it so that we win. There are 2 ways. There are going to be 2 ways. What are the 2 ways? Let's try to figure it out. If you have to see that what 3 sticks won't be able to form a triangle, then you can play with this property. You can play with this property. The property says that if you have a triangle with length of sides or sides of length A, B, C, then for each side, the sum of the other 2 sides should be greater than the current side. That is, B plus C should be greater than A plus C should be greater than B, A plus B should be greater than C. If any one of these 3 conditions violate, you won't be able to form a triangle. Okay. For example, in 4 to 10, if you see 4 plus 10 was greater than 2, good to go. 10 plus 4 was, if you see 2 plus 10 was greater than 4. 4 plus 10 was greater than 2. But 4 plus 2 was not greater than 10. Hence, we won't be able to form a triangle like this. If you will try to draw a triangle like this, you won't be able to draw. Now, if you see here, then One possibility with which you won't be able to form a triangle can be 269. Why 269? Because here if you see 269, then 2 plus 6 is not greater than 9. So for this side the condition violate, and hence we won't be able to form a triangle. So one way is 269. Let's try to figure out another way. So if you keep 5 to 9, then also 5 plus 2 is not greater than 9, and hence this is going to be another way, 5 to 9. Okay, now you might feel that okay, then though in any case will it can it form any triangle? Yes, there are few ways in which it can form a triangle. For example, if you keep 5 6 9, see, 5 plus 6 is greater than 9, 5 plus 9 is greater than 6, 6 plus 9 is greater than 5. So here you can form a triangle, but in these two ways you won't be able to form a triangle. Hence the answer for this test case is going to be 2. Answer for this test case is going to be 1, because there is only one possibility and that possibility also doesn't work. So you will be given an array of length n, right? You will be given an integer array, and you need to figure out how many triplets can be formed. How many triplets can be formed if we want to make sure they don't form a triangle. Okay, they don't form a triangle. This is the question in front of us. Now one brute force approach can be what? If I try to go for a brute force, then the brute force approach can say that form all possible triplets. Can I say that? One brute force approach can be to form all possible triplets, right? If you can somehow form all possible triplets, in that case you can configure every possible triplet to try to form these three relations and then check whether all three relations work or not. Because even if one relation falls, we won't be able to form a triangle. All three relations should work out. Okay, but the problem here is the length of the array can be as big as 2 into 10 raised power 3. And to form all possible triplets, if there were all possible pairs, it takes us n square. If we have to form all possible triplets, it will take us order of n cube. Order of n cube will not be submitted. This will give you time limit exceeded. This will give you time limit exceeded. This problem won't be submitted, right? Can we somehow optimize? Now the optimization is hidden behind this thing, that there should be a pair of elements such that the sum of the elements is not greater than some third element, or you can write it like there should be a pair that should be less than a particular value c. All those triplets that follow this rule are our answers. Can I say that? Because if there is a triplet that follows this rule that sum of the two elements is less than c, then technically we will be able to say that this triplet can never form a triangle, right? Whatever permutation you take, this triplet cannot form a triangle. We have to just find this particular part, right? Okay. Now how can we do this? How can we do this? We have an array. We have an array. Inside that array, right? Now we need to find triplets such that they follow this condition. Okay. Now, can you see here that we need to find a pair of element that is less than the third element? If I simplify this statement, we need to find all such C for which A plus B is less than C. Can I say that? If we can somehow find all the values of C such that A plus B is less than C, such that A plus B is less than C, then we can technically solve this question, right? Okay. Now, for the time being, if I assume that this is a sorted array, and if I have a value x, then we learned an algorithm called as upper bound. What is upper bound? Upper bound gives us the first index greater than x, right? So let's say some index a of j, this is the upper bound for x, right? That this is the first index greater than x. If this is the first index greater than x, everything to the right of it is also going to be greater than x. Can I say that? For example, if you see 5296, okay, if I sort 5296, you will get 2569, okay. If I say that x is equals to 7, or let's take even less value, x is equals to 4, and I want to find the first value greater than 4. First value greater than 4 is going to be this 5. Now everything to the right of 5 is also going to be greater than 4. Can I say that? Right. So if in the original problem we have to find a triplet that follows this condition such that a plus b is less than c, then can I say that for all possible pair a comma b, if we find a c such that a plus b is less than c, then we can do something. Can I say that? Right. This is what a plus b, right? I have to pick 3 elements from the array. How about if I try to form all possible pairs? If I try to form all possible pairs in the given array, right? Let me take a bigger array. Okay? And let me take a bigger sorted array. One, 3, 4, 6, 12, 18. Okay. Now I say that if I want to pick all the possible triplets in this array such that a plus b is less than c, then first of all, let's try to form all possible pairs. First step, form all possible pairs. Now, forming all possible pairs is very easy, right? We know that this thing can be done in order of n square. In order of n square, we can do that, and n is 10 raised to the power 3. So 10 raised to the power 3 square is going to be approximately 10 raised to the power 6. This is doable. So for example, we keep I here, we keep j here. This is the first pair 1 comma 3, right? First pair is 1 comma 3. What is 1 plus 3? 1 plus 3 is 4. So I need to find the first index greater than 4. So if I try to find the upper bound, of 1 plus 3, I'll get the upper bound of 1 plus 3 to be 6, right? That means if I make a pair of 1, 3, 6, 1, 3, 12, 1, 3, 18, all these 3 pairs are never going to form a triangle. Can I say that? All these 3 pairs won't form a triangle such that 1 comma 3 are the 2 selected elements. Now the next pair can be what? 1 comma 4. We repeat the same process. This time sum is what? 1 plus 4, 5. I want to find the upper bound of 5. Upper bound of 5 is again this 6. So I will say that 1, 4, 6, 1, 4, 12, 1, 4, 18. All these 3 are also not going to form a triangle. Let's move forward with j to be here. 1 plus 6. 1 plus 6 is 7. Upper bound of 7 is this. So 1, 6, 12 and 18. Right, 1, 6, 12 will be one pair. 1, 6, 18 will be one pair. So 2 more pair you found. 1, 6, 12. 1, 6, 18. Next element 12. 12 plus 1 is what? 13. So 1, 12, 18, because the upper bound is going to be 18, right? That's it. You don't need to go here. Now I moves here, j moves here. Okay, this is 3 plus 4. We have fixed the pair to be 3 comma 4. So 3 plus 4 is 7. What is the upper bound of 7? This element 12. That means 3, 4, 12 and 3, 4, 18. Both of these are going to be also the part of our answer, because sum of 3 plus 4 is also less than 12 and less than 18, and so on. So for every pair, calculate the upper bound of the sum of the pair, right? You calculate the upper bound. Let's say the upper bound comes as some index j. Okay, upper bound, or let's say not say j, let's say index k. Upper bound comes as some index k. So if you see, when I and j were here, upper bound was what? This. So how many, sorry, upper bound was this. So how many pairs it contributed? It contributed 3 pairs. Can I say that? It contributed 3 pairs, right? So how do we calculate it? If this index is k, what is this k? 0, 1, 2, 3, right? 0, 1, 2, 3. And the length of the array is what? 6. 6 minus k is what? 3. So add n minus k to your answer, right? N minus k to your answer. What will be the time complexity of this approach? To calculate all possible pairs, you did n square. Once the pair is calculated, you are on a current pair. On the remaining array, you apply upper bound. Upper bound works in log n. So the time complexity of the solution becomes order of n square log n. And if n is 10 raised power 3, n square log n is what? 10 raised power 6 into log of 10 raised power 3. 4 into 10 raised power 6. This is going to be 4 into 10 raised power 6 into 10. This is 4 into 10 raised power 7, which is less than 10 raised to the power 8. This solution will be submitted. Can I say that? A direct application of upper bound functionality. And then there is one variation. There is a variation. We also need to, let's say, include / exclude degenerate triangles, right? There can be a corner case of degenerate triangles. So in degenerate triangles, you have a plus b equal to c, right? When the three dots are overlapping, the area of the triangle is actually 0. That's a degenerate triangle. So if somebody says that exclude degenerate triangles, right? That means the 3 sticks that you pick, if they form a degenerate triangle, then also you win, the other person loses, right? So instead of just checking a plus b less than c, you have to also check a plus b less than or equal to c, right? Because now degenerate triangles also make you win. So for example, 1, 3, 4 is going to make a degenerate triangle. So if you have to c less than or equal to c, or you say c is greater than or equal to a plus b, so you need to find the first value which is either greater than a plus b or equal to a plus b. Then instead of upper bound, you have to consider lower bound, right? But if the question says that the degenerate triangles make you lose, right? That is, include degenerate triangles in the excluded set of triangles, then upper bound works directly, right? So based on the corner case, whatever you have, you can just work it like that. One small step that you have to do in the beginning is sort the array, because the array might be unsorted. You need to manually sort the array. Sorting the array will separately take n log n. So n square log n plus n log n is n square log n only, right? So just sort the array, calculate with all the pairs. With each pair, calculate upper bound. That is going to be your answer. So I'm assuming that you will do somehow ARR dot sort. Okay. And then you will do for I equals to 0, I less than n, I plus plus. For j equals to I plus 1, j less than n, j plus plus. Okay. Now, sum is what? A of I plus A of j. Right. You calculate the upper bound. So k is equals to upper bound of a comma. Now this upper bound that you have to find, you don't need to find in the whole array. You don't need to find on the whole array. You need to find this upper bound on the right side of j. On the right side of j, right? You don't need to find this upper bound on the whole array. So either you can manipulate it like that, or of course, even if you don't manipulate it, then the sum is always going to be on the right side only. So even if you just call the upper bound on the whole array, then also these two elements are of course going to be discarded because their sum is always greater than them. So for the timing, just call upper bound on the whole array, no problem. Pass the sum based on which you have to calculate the upper bound. And then you do answer plus is equals to n minus k. Right, that's it. Return answer. So if you have the implementation of upper bound already with you, this solution is going to work in order of n square log n. Space complexity is order of 1 because you're not taking any extra space, or we should say the space complexity is going to be the space complexity of the sorting algorithm, because maybe the sorting algorithm is taking some extra space. So I hope this basic algorithmic implementation is clear to everyone. So this is a new problem coming in front of you from lead code, problem number 350, intersection of two arrays, marked as easy. I will say it is also easy. More than 6,000 upvotes and previously asked in multiple companies: Amazon, Facebook, Uber, Bloomberg, Adobe, LinkedIn, Nutanix, Google, Apple, right? You have been given two integer arrays, nums1 and nums2. So you have the access to two integer arrays. They can be of different length. You need to return the array of their intersection. So you need to return a new array such that whatever are the common elements in both the arrays, you return the common elements. Each element in the result must appear as many times as it is shown in both the arrays, and you may return the result in any order. Okay. So if let's say in the first array 2 is present 2 times, and in the second array also 2 is present 2 times, and then in their answer also 2 should be present 2 times, and you have to return the common elements. How can you solve this question? It's a very easy question. One quick solution can be brute force. You have the first array, right? Start with every element of the first array. Pick the first element and do a linear search of the element in the second array, right? Do the linear search of the element in the second array. Somehow try to do something like this. Okay. So that when you go to every element, you are able to do linear search for it, right? Now the problem that you can face here is that for this 2, let's say if there is only one occurrence, of 2, then technically for this 2 also you will try to see that, oh, this is the same occurrence, right? In order to avoid that, for this 2, whenever you find an element that is equal to the current element, you can try to modify it. You can try to maybe modify it with, let's say, plus infinity or something, so that if another element tries to search for it, it doesn't get it. Okay, cool. Apart from that, there is another solution that you can build that is using frequency map. That is very easy solution to think of. Just prepare the frequency of any one array. 1 is present 2 times, 2 is present 2 times, and then iterate on the second array. If you find an element here, reduce the frequency of that element and add that in your final answer. That is something that you can do. In this solution, you are going to take order of n time, but you are going to take order of n space also, right? It's a very efficient solution, no problem at all. Sometimes you might be asked to optimize the solution. In that case, The thing that you are doing using linear search, you can optimize it using binary search. Okay. Using binary search, what you can do, for every element, let's say this is the current element, right? So in the given array, try to find the lower bound and the upper bound for this element. And in this array also, try to find the lower bound and upper bound. Okay. If let's say lower bound is this, upper bound is this, here the lower bound is this, upper bound is going to be outside of the array. Just calculate using upper bound and lower bound, you can find, right, that how many occurrences of 2 are there. How many occurrences of 2 are there. Using this lower bound and upper bound, you can find out how many occurrences of 2 are there. Whatever is the minimum value, that many number of 2's you have to add in your final array. And then skip 2 altogether. Don't do the same task again for any other 2. Right. But before you actually do that, you need to sort both the arrays. Sorting is going to take n log n time. So the time complexity of this solution is going to be order of n log n. Space complexity will depend on what is the complexity of the sorting algorithm. But here you will definitely optimize over the order of n space that you are using for frequency map. So for example, if you have something like 1, 3, 3, 1, 3, 2, 8, and let's say here you have 3, 1, 2, 3, 2. Okay, you can sort both the arrays. So both the arrays become something like this. This becomes 1, 2, 2, 3, 3. Okay. Then let's say the current element is 1. Okay. This one. Try to find the upper bound and lower bound in this array. Upper bound and lower bound in this array. So upper bound is, sorry, lower bound is this. Upper bound is this. Lower bound is this. Upper bound is this. Upper bound minus lower bound is going to tell you how many occurrences of 1 are there is in the first array. How many occurrences of 1 is there in the second array. Minimum of both of them is 1. So in your final answer, 1 occurrence of 1 is going to go. And then you keep moving your current pointer till the time the current element is changed. Now the current element is different than 1. Current becomes 2. You again do the same thing, upper bound and lower bound. So lower bound, upper bound, lower bound, upper bound. What is the minimum of both of them? This is 1. This frequency is 2. Minimum is 1. So you need 1 occurrence of 2 here. And then you keep on moving forward till the time it is different than 2. This becomes 3. Now again upper bound, lower bound. So upper bound goes here, lower bound goes here. Upper bound goes here, lower bound goes here. So how many occurrences of 3 we have here? 3. How many occurrences of 3 we have here? 2. So 2 occurrences of 3 we need to add. And then we move forward. Current becomes 8. Current becomes 8. Lower bound and upper bound. So lower bound, upper bound. Here lower bound, upper bound, both of them outside. So this becomes 1, this becomes 0. Minimum of both of them is 0. So no occurrence of 8 should go. And that's it. So the time complexity is going to be order of n log n because sorting takes n log n. And then for every element, you are doing upper bound, lower bound for every element, right? So upper bound, lower bound for 1, upper bound, lower bound for 1. So 4 times you are applying binary search per element approx. So if there are n elements, 4 times binary search is n into 4 log n, that is n log n. So the time complexity remains n log n, but the space complexity has been optimized to whatever space the sorting algorithm is taking. So this is going to be the very simple solution that you can build up for this particular question. There can be more solutions to it. There are some data structures like set and all using also with which you can solve this question. But I believe this is a fairly easy and a good starter problem to explore on LeetCode. And I would recommend you guys to definitely try to code it as well. So there is this another problem number 349, intersection of two arrays. The only difference between this question and the last question is that if there is intersection of any two elements, then you don't need to insert every occurrence of that element, right? All you need to do is just add one occurrence of that element. So in the same binary search based approach, what you can do, you can find whether that upper bound minus lower bound is at least 1 in both the arrays or not. If it is, just add single occurrence of that element and then move forward. You don't need to add multiple occurrences of that element. That is the only difference between this problem and that problem. Similarly, frequency map can also be used to solve this question, and even brute force can be used, right? So both of the problems are same and the implementation are just slightly different. Both of them can be solved by sorting and searching based approaches. So this is a new question coming from lead code, problem number 162, peak element. This is one of the most interesting problems that you will find on binary search on lead code, because as I always mention about the definition of binary search, that binary search is not an algorithm that is just applicable on, let's say, sorted situations. There can be some specific scenarios in which for unsorted situations as well, binary search works like a charm. And this is one of those. This is actually one of those. Okay. So this is problem number 162. You can see 11,500 upvotes, right? And if you carefully see what all companies this has been asked in, it's asked in Facebook, Amazon, Adobe, TikTok, Uber, Google, Bloomberg. You can see Microsoft, Walmart, every big tech has asked this. And an interesting fact about this particular problem is that this was asked in my first full-time engineering interview for a company as well, right? I interviewed for Interview Bit, and there I was asked this particular question in the first face-to-face round. So let's just start the discussion on this particular question. So the question says that a peak element is an element that is strictly greater than its neighbors. Okay. So here they are actually defining the definition of peak element, that let's say if you want to define peak element, then a peak element is an element which is strictly greater than its neighbors. For example, let's say you have something like 11, 12, 10. So if you carefully see 12, 12 is greater than 11 and greater than 10, and that too strictly greater. That means it's not equal to, it's just like greater than both of the values. That's a peak element, that if your element is greater than its neighbors, it is qualified as a peak element. So in this case, 12 is a peak element. Now, given a zero indexed integer array nums, find a peak element. So what you have been given is, you have been given a zero indexed integer array, right? The given integer array is zero based indexed, and you need to find a peak element and return the index. So in the given collection of numbers, you are actually expected to find the peak element and tell the index corresponding to that. Okay. If the array contains multiple peaks, then return the index of any one of the peaks. So in case the array contains multiple peaks, that let's say there are multiple peak available, then what you are expected to do is, you are expected to just return any of the corresponding peaks available. You may imagine that nums of -1 is equals to nums of n is equals to minus infinity. That is, generally you have indexes from 0 to n minus 1, because in an n length array, you have indexes from 0 to n minus 1. Now what they actually tell you is that, for example, let's say you have a case like this, 1, 2, 3, 4, 5. Okay. Now here you can see 5 is greater than 4, right? But 5 has nothing to the right of it, because 5 is the last element. So in that case, if you carefully see, what is the index of 5? Index of 5 is n minus 1. So what they are suggesting is that you can expect that after the last element of the array, you have minus infinity, and before the first element of the array, you have minus infinity. Okay. In other words, an element is always considered to be strictly greater than neighbor that is outside the array. You must write an algorithm that can find it in log of n time. Okay. So let's see. So what the author suggests is that, let's take this example. I'm writing this particular example on my iPad. Okay, just a second. 1, 2, 1, 3, 5, 6, 4. Okay. So this is the given array. This is the given array, and the size of the array is n. It's an n length array. If you take a look at the constraints, n can be as big as 1000, but an interesting part is that they are expecting us to figure out a log n algorithm. Okay. Now what the question says is that you need to find something like a peak. Okay. You need to find something like a peak element. Peak element. What's a peak element? If let's say, if you consider nums at I as the peak element, right? then its value should be greater than nums at I plus 1 and nums at I minus 1, right? Its value should be greater than both of these things. Now, you might be thinking that, okay, what about the elements at the terminal ends? Like 1 has nothing on the left, 4 has nothing on the right. So for that case only, they are explaining that to the left of 0 and to the right of n minus 1, you can expect minus infinity. So here you can expect a minus infinity, here you can expect a minus infinity, just for making sure your calculations are relatively easy. Okay, and you need to find this element. Now, an interesting part about this whole question is that the given array is unsorted. You can see there is no information about the fact that the array is sorted or not, and you can see in the examples also it's an unsorted array, and you cannot apply any sorting algorithm. For example, if you will apply a sorting algorithm like merge sort, quick sort, it will take n log n time, right? That is more than the expected time complexity of log n. So you need to solve this question in log n time complexity, and that is why you cannot manually sort this array. If you cannot manually sort or anything, so in this unsorted situation, you need to find a peak element. And for these kind of scenarios, binary search comes very handy, right? So whenever you see that the expected complexity is around log of n, binary search is a fair choice. Binary search is a fair choice because it directly gives you a complexity of log n. There are other algorithms also that can help you to achieve log n, but binary search becomes a good candidate, right? Now, one more problem that can occur after sorting is that if after sorting, the order of the elements will change, so you won't be having access to the original index of the corresponding element. Now, how can you actually solve this question? Brute force we have discussed, like you can like maybe sort the array, or maybe manually just in order of n time complexity, you can linearly go to every element and check to the right of it and to the left of it. Okay, that's an ON algorithm also, but we need to find something optimized. Okay, cool. Now you can see the question says that if the array contains multiple peaks, return the index of any one of the peaks. Now this is the interesting part. Now just think about it. If let's say the array is this only, I'll copy this content, paste. Okay, now what I'll help you to do is I'll help you draw a graph. Okay, let's try to draw a graph, guys. It will help us to get an understanding better. Okay, let's say this is 1 2 3 4 5 6. Okay, so we have the first element at 1, right? We have the second element at 2, third element at 1, then we have 3, then we have 5, then we have 6, and then we have 4. Okay, these are the elements, right? Let's connect them via straight lines so that we can see the graph in hand. Okay, so this is the graph that we will be able to actually plot if we try to use the same test case, this given test case, if we try to visualize. Now, an interesting part here is that this graph shows the fact that the array is unsorted, right? Now, if you carefully see, in this particular question, there are two peaks, this one and this one, right? There is one peak here, there is one peak here. Okay, and you can return any one of them. You can return any one of them. Now, I would like to tell you some simpler cases first. Like this is a case of unsorted array, right? For unsorted array, we will try to find it. But how about if the given array was a sorted array? If the given array was a sorted array, then how the graph would look like? If the given array would have been a sorted array, the graph would look like either this, or it will look like, let me plot it again, or it is going to look like this. Can I say that? Right? So for sorted situations, sorted array, right? You can see that maybe the data will be all in increasing order, or the data will be all in decreasing order. right? Okay. Now, if let's say you are given a sorted array like 1, 2, 3, 4, 5, what will be the peak element? Can I say in the sorted situations, the last element will be the peak. The last element will be the peak, right? And here as well, the first element is the peak. Can I say that? Why the last element is the peak? Because just think about it. The last element is greater than the second last element, and we know that to the right of last element we can expect minus infinity. So you can already see that this makes a peak, right? This makes a peak. And here also, before the first element also there is minus infinity. So this first element is greater than the second element already, so this also becomes a peak. So what we are able to see here is that if you have a sorted scenarios, then your terminal elements make the peak, right? Your terminal elements make the peak. So it's a straightforward test case, right? So for example, here you have 5, 4, 3, 2, 1. So in this case, 5 is your answer. And here you have 1, 2, 3, 4, 5. Then also 5 is your answer. One is to the rightmost, one is to the leftmost. Okay. Now an interesting part that I can propose is that don't you not think that the unsorted array is technically a collection of a sorted array, sorted array, sorted array, and a sorted array, right? Can I say an unsorted array is kind of like the collection of multiple unsorted regions? Can I say that? Right? If that is the case, then just think about it. If we have a very general scenario, right? If we have a very general unsorted array like this, okay? Let's say we have a unsorted situation like this. Okay, let's say this is the plot of the graph. This is the plot of the graph that we are getting, right? Let's assume that this is the unsorted array. Now just think about it. If you randomly pick an element inside this unsorted array, right, then maybe the element will be on a decreasing curve or the element will be on an increasing curve. Can I say that? For example, let's say I randomly pick 3. Can I say 3 is a part of an increasing curve? We can call this as an increasing curve, and we can call this as a decreasing curve. Can I say that? Right. So if you randomly pick an element, anywhere, right? If you randomly pick element anywhere, it is going to be part of either an increasing curve or a decreasing curve. Can I say that? Every element can be considered part of an increasing or decreasing curve. Can I say that? For example, if I take this 4, can I say 4 is a part of the decreasing curve? If I take this 2 is, let's say, a part of an increasing curve. In fact, 2 can also be considered as a part of a decreasing curve, and so on. So every element is either a part of an increasing curve or they are a part of a decreasing curve. Can I say that? If that is the case, then how about if somehow we can actually detect that whether the element is part of an unsorted region, whether the element is part of a increasing curve region or a decreasing curve region? How about that? How about we find whether the element is part of increasing or decreasing curve, right? Let's say you randomly pick an element and then you try to figure out whether the element is part of a increasing sequence or a decreasing sequence, increasing curve or a decreasing curve. Now you might be thinking, sir, how is that going to help? Just think about it. If let's say your element is on an increasing curve, then we know the fact that in an increasing curve, on the rightmost element you have a peak. So can I say if 3 is a part of an increasing curve, then we are definitely sure, if an element is a part of an increasing curve, then we are definitely sure that no matter what is on the left, but definitely on the right side, there is a peak element. Can I say that? Right? Let me repeat it again. If an element is on an increasing curve, for example, here, or for example, here, then I don't know what's on the left. For example, on the left side of it, there is no peak. So I don't know what is on the left, but I am definitely sure that if an element is on an increasing peak or an increasing curve, the peak lie on the right side. Somewhere on the right side of this element, there will be a peak. Can I say that? So, and same thing for the opposite order. For example, you are on a decreasing curve. I don't know what happens on a right side of a decreasing curve. I do not know on the right side. But for a decreasing curve, if you are on decreasing curve, then we are definitely sure that on the left side, you will definitely find a peak element. Can I say that? So what I can say is that if you are on an increasing curve, then on your right side, always your peak is present, but you are not sure about the left side. And if you are on a decreasing curve, then on your left side, you have a peak element, but you are not sure about the right side. Can I say that? This is going to be the basis of everything. This is going to be the basis on which we are going to actually decide where our element is, right? So what I'm trying to say is that how about we consider this whole array as a search space and we divide our array into equal halves, right? So for example, okay, so we divide our array into equal halves, we get 3. This is a midpoint, right? This is a midpoint. First of all, we can eventually check that is my midpoint the peak? Is my midpoint the peak? Right? How can you check? You can compare the midpoint with the adjacent elements. So you can see this is not the peak. If the midpoint is not the peak, then you can try to detect whether the midpoint is on an increasing curve or the midpoint is on a decreasing curve. Can I say that? How can you realize? How can you realize whether the midpoint is on an increasing curve? How can you realize that? You can very easily realize that with the fact that if let's say the current element is lesser than the next element, then you are on an increasing curve, right? If your current element is lesser than the next element, you are on an increasing curve. Can I say that? Think about it. Is 3 less than 5? 5 is the next element. Yes. 3 is less than 5. So can I say that 3 and 5 are going to make an increasing curve? So definitely 3 is a part of an increasing curve. Can I say that? Right? Think about it. If let's say we would have got 1 like this. 1 is a part of increasing curve here. We can say that. Right? So you just compare that if a of mid is less than a of mid plus 1, then you are a part of an increasing curve. Otherwise, you are a part of a decreasing curve. Can I say that? Now, sometimes you might feel that, okay, 1 can also be part of a decreasing curve, right? So for these cases, you can judge it like anything. Even if you consider 1 as a part of a decreasing curve, then also we will be able to find the answer. No problem there. So that is why I'm just keeping this as the comparison criteria. Now, 3 is a part of a increasing curve. Now, if 3 is a part of an increasing curve, we are definitely sure that on the right side, we will find some peak, but we are not sure about the left side. And this is going to be the partition criteria. This is going to be the criteria based on which we can actually divide our search space into 2 halves. See, we are able to divide our search space into 2 halves where we know that in one half there can never be the answer, but in the other half there definitely will be the answer. So we are going to eliminate the left side and go to the right side. If you go to the right side, this becomes low and this is your high. Okay, this becomes low and this is your high. Now again you calculate the midpoint, and this time the midpoint that you calculate is 6, and 6 is already your peak element. Can I say that? Right? You can see 6 is already your peak element. So you got your answer. Now let's take one more example. Let's take one more example, and this time let's take pretty random example. Okay. So let's say 1, 3, 0, 6, 5, 2, 7, 1, 2, 5. Okay. I took some random numbers. Let's try to plot them. Let's try to plot them, guys. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Okay, cool. So let's plot it. So 1, 3, 0, 6, 5, 2, and 7, 1, 2, 5. Okay. This is how the graph looks like. This is how the graph looks like. Pretty random, right? Pretty random. Okay. This is how the graph looks like. Now, what I'm going to do is we will divide our search space into two halves. Right? I will consider the whole array as my search space. So 9 plus 0 by 2, this is low, this is high. 9 plus 0 by 2 is 4, this is mid. Okay. So we are at 5. We are at this value. Can I say that? Now you can see this is on a decreasing curve. If you're, and how do you know that this is on a decreasing curve? You compare mid with mid plus 1. You can see 5 is less than 2. That means 5 is on a decreasing curve. If you are on a decreasing curve, then I'm not sure about the right side, because maybe on the right side there were no more greater elements. For example, on the right side everything was a 0. So on the right side we are not sure whether we will find the element or not. But on the left side we are definitely sure about the fact that there will be at least one peak because of this scenario. So what I'll do is I'll do high is equals to mid minus 1. Now again we'll calculate the mid. 3 plus 0 by 2 is 1. This is mid. Okay. Now we are at 3. Now you can see that 3 is eventually a, you can say, peak element. We found one more peak element, right? So you can return any peak element. Now just think about it. For a moment, what I'm going to do is I'm going to swap 3 and 0. Okay. And so the curve will look something like this. 0 and 3. Okay. So just to give you a better context. 3. Okay. Let's plot it. Okay, cool. Now, if this would have been the array and we would have got to the left half, now you can see the midpoint is at 0. Now you can see the midpoint is at 0. Now, you might feel, oh, this 0 can be a part of the decreasing or increasing both kind of a curve. So you can consider it in any one. So I'll again consider by comparing mid with mid plus 1. Is 0 less than 3? Yes. That means it is a part of a increasing curve. So just think about it. If 0 is a part of an increasing curve, we are not sure about the left side, but we are sure about the right side. So what we are going to do? We are going to say low is equals to mid plus 1. Right? So whenever you have these kind of elements, right, which are in itself kind of like a peak but in a negative direction, you can consider them in increasing, decreasing, any curve. It will not matter a lot. Now, you are between 3 and 6. Midpoint, 3 plus 2 by 2 is 2. This is your mid. Right, this is your midpoint. So again, you are here. Is this on an increasing curve? Yes. This is on an increasing curve. That means we are not sure about the left side, but on the right side, we will definitely find the element. So you'll do low is equals to mid plus 1. And now you can see low and high both are pointing to 6. Midpoint is also 6. And you can very easily realize that 6 is a peak element. And that's how you can actually particularly solve this question, right? So what is the time complexity? The time complexity of this particular algorithm is order of log n, and the space complexity of the log or algorithm is order of 1, because we are not taking any extra space. And you can see now in an unsorted situation, in an unsorted array, very easily we are able to apply binary search. So this thought process that a lot of people have inside, that binary search is only applicable to sorted array, is absolutely wrong. There can be situations where in unsorted situations as well, binary search can come handy. Now, if you want to code this particular solution, you can see I have a code prepared already, and we can try to actually discuss about how exactly things are working. You can see here I am actually defining my search space. Defining search space. We know that our peak element is going to be one of the elements of the array only. So I keep the low on 0 and high on nums.length minus 1. Okay. And then we start applying binary search. We calculate the mid. The moment you calculate the mid, the moment you calculate the mid, you need to figure out whether mid is on increasing or decreasing curve, right? This is the question that you have to figure out, right? So you can see, first of all, I am keeping a check that the midpoint that I found is not the last index, right? This check here tells me that mid is not the last index, because if the mid is the last index, just think about it. If somehow you started converging your binary search and you realize that your midpoint is the last index, then you will not be able to get mid plus 1, right? You will never be able to get mid plus 1. Can I say that? Just think about it. If you have an array and mid becomes the last index of your array, then you do not have mid plus 1, right? Mid plus 1 does not exist. So this check is to consider the fact that if mid is somewhere in between the array and the value at mid is less than the value at mid plus 1, that means you are on an increasing curve. If this condition is true, if true, then mid is on increasing curve. Can I say that? Right? If mid is on an increasing curve, then we know that on the left side we are not sure whether the element will be there or not, but on the right side we are definitely sure. So how do you go from, you avoid left side and go to the right side? You do low is equals to mid plus 1. So you can see low is equals to mid plus 1. Else, if you are on a decreasing curve, now if you want to check if you are on a decreasing curve, either you can compare it with mid plus 1 also, or maybe you can compare it with mid minus 1 also. Anything you can do, right? Like this comparison you can do with mid plus 1, mid minus 1, anything. So if you are doing with mid plus 1, then you do not need this check. But if you are doing with mid minus 1, then you need to check whether you are the first element or not. Because if, let's say, you are the 0th index of the array, then you do not have 0 minus 1. So you are going to check if you are the 0th index of the array or you are on a decreasing curve. That means mid is greater than mid minus 1. Then you are on a decreasing curve. If you are on a decreasing curve, then we are not sure about the right side, but on the left side we definitely know we have the answer. So we go right is equals to mid minus 1. So this is to check. If true, we are on decreasing curve. And again, you can again use mid plus 1 only to compare it. No problem there. You can use mid plus 1 to compare it. Absolutely no problem at all. And at last, what you can do is you can actually return the answer. You can see one thing is actually missing in this particular code. What is the missing part? Now the missing part comes with the fact that you put a check here that if mid is peak, maybe the mid element is the peak element, right? How can you put a check of if mid is the peak or not? You can check if mid is equals to 0 and nums of mid is greater than nums of mid plus 1, right? Nums of mid plus 1. Can I say that if the midpoint you got is the 0th index, right? That means the 0th index of the array. You just compare it with the first index. If this value is greater than the first index value, then mid is a peak. Or if mid is equals to n minus 1 and nums of mid is greater than nums of mid minus 1, right? Just think about it. If you are the last element and you are greater than your previous element, then also mid is the answer. Or nums at mid is greater than nums at mid minus 1 and nums at mid is greater than nums at mid plus 1. Can I say that? The third condition is if you are somewhere in the middle. And your mid element is greater than the left part and the right part, then mid is your answer. You can actually implement this as well. So what I'll say is, let's do it here. What I'll say is that if mid is equals to 0 and nums of mid is greater than nums of mid plus 1, then your answer is mid. Then your answer is mid. Can I say that? Sorry, we need to put it here. We need to put it here. Okay. Otherwise, if mid is equals to nums dot length minus 1 and nums of mid is greater than nums of mid minus 1, then also you return mid. Otherwise, if nums of mid is greater than nums of mid plus 1 and nums of mid is greater than nums of mid minus 1. If any of these three conditions are true, mid is your answer. Can I say that? If any one of these conditions are true, mid is your answer, right? This is for leftmost element being peak. This is for rightmost element being peak. And this is some internal element being peak. Right? That's it. That's how you can actually solve this answer. And at last, if like at last you can just return, let's say -1 or something, because eventually you will be always able to find a midpoint altogether. Right? This is something that you can actually do. Right? And this same checks, if let's say you are coding in JS, these same checks you can put here as well. Don't need answer as of now. And these same checks will work. Okay. So same checks will work here as well. Right? And that's it. That's how you can actually solve the problem of peak element. Now there is a small corner case that is coming up. You can see, what if there is a single length array? In a single length array, these two conditions are not going to work. These two conditions are not going to work. Okay. So you can have a separate check here that if, and you can actually visualize this with the fact that in the constraints also it is given that there can be a single element. So if nums dot length is equals to 1, you don't need to do anything. You just return nums of 0, right? If nums dot length is equals to 1, you do not need to do anything else. Just return the 0th index. That should actually work. Let's try to submit it now. Let's see. Oh, they expect it to be 0 because we need to return the index, not the element. We need to return the index, right? So let's run the code. Let's submit the code, and here also, instead of element, we need to return the index. So we'll do 0. And you can see this has got submitted. And this same check, maybe I can apply for a JS solution as well. And let's try to submit the JS solution. Submit. And you can see JS solution also works. So you can see things are working pretty fine for us. And that's how you can actually implement the peak element with all the corner cases handled. So this is a new question coming from lead code, problem number 875, cocoa eating bananas. The problem is marked as medium, 10,000 plus upvotes, you can see. Previously asked in Amazon, DoorDash, Facebook, Google, Adobe, Apple, Yahoo, Deutsche Bank, Uber, Salesforce, RCZM, all the big techs. Right. It says that Coco loves to eat bananas. There are n piles of bananas. So how does a pile of banana looks like? So let's say you can understand pile as a box of banana. Okay. So this is one pile of banana. This is one more pile of banana, one more pile of banana, one more pile of banana, and so on. What is this? This is piles of banana. You can say box of banana also, where you have a collection of bananas stored. Okay, that's a pile. So generally pile is something like you put one banana, on the top of that banana you put one more, and so on. For example, if somewhere you write piles of coins, It looks like this. Pile of coin is like this. One coin on the top of another, on the top of another, on the top of another, and so on. That's a pile of coin. Similar to that, you have pile of bananas. Okay. The ith pile has piles at I number of bananas. So there is an array given to you. And this array represents that what is the number of banana on the ith pile. For example, on the 0th pile, you have 3 bananas. On the first pile, you have 6 bananas. On the second pile, you have 7 bananas. On the third pile, you have 11 bananas. Now here you can see quantity of banana per pile is given to you. The guards have gone and will come back in H hours. So there are some guards guarding the pile of bananas, and these guards are going to come back in H hours. In H hours, right? Okay. Coco can decide her bananas per hour eating speed of K. So there is a value K that Coco can decide. What does K represent? K represents how many bananas per hour Coco can eat. Each hour, she chooses some pile of bananas and eats K banana from that pile. Okay, so K represents your eating speed. What is the eating speed? Banana per hour. So what, let's say she chose K some random value. So what she will be able to do is that she will choose any one of the pile of bananas and will eat K bananas from that pile. For example, let's say Coco chooses the speed as 4 banana per hour. And let's say she chose this pile. So what she will be able to do in 1 hour, she will be able to eat 4 bananas from this pile, and this pile will be left with 7 bananas only. If the pile has less than K bananas, for example, Coco chose the speed as 4, and you can see this pile has not even 4 bananas, then she will eat all of them. So she will eat all 3. She will be having some time left, but she will not eat more bananas during this hour. So if she decided that I am going to eat only 4 bananas, and if a pile has less than 4 bananas, so she will eat that whole pile and not eat anything else. Coco likes to eat slowly, but still wants to finish eating all the bananas. You want to find the minimum speed such that she can eat all the bananas with H hours. So you need to figure out the minimum possible speed with which she can actually eat all the corresponding bananas, right? Okay. You can see these are the test cases given to you. And if you see the constraints, the number of elements in the piles is 10 raised to the power 4. Piles length and H can be as big as 10 raised to the power 9. Okay. So, and every element of the pile can be as big as 10 raised to the power 9. And you need to figure out the minimum speed with which Coco can start actually eating. Now, just think about it. If let's say we want to implement a brute force solution, what do we have to do? We have to find minimum value of K. Find minimum value of K. And what is K? Banana per hour eating speed. So you need to find the minimum speed with which she should eat the bananas such that all the bananas are done before the guards can come. Right? Okay. Now, what will the brute force? The brute force will be to try all possible values of K and check if Coco can eat bananas or not. Can I say that? Right. So the brute force will be to try all possible values of K. What are the possible values of K? The possible values of K is like if she eats 1 banana per hour, if she eats 2 banana per hour, if she eats 3 banana per hour, 4 banana per hour, 5 banana per hour, 6 banana per hour, 7 banana per hour, 8 banana per hour, and so on. And for each possible value of K, you try to figure out can she eat the banana or not. Okay. Now you can already see this is going to take a lot of time. Why? Because if she eats 1 banana per hour, then what do you have to figure out? In this whole area, you have to figure out that if the speed is 1 banana per hour, how much time it is required to eat all the bananas. Then you go to 2 bananas per hour. That if the speed is 2 bananas per hour, how much time it is required to, I would say, eat all the bananas in the array, and so on. So you can see already this is very time consuming. But this brute force solution is going to help us optimize itself as well. Why? Just think about it. If let's say you have a value mid and you want to check if by having mid banana per hour speed, Coco can eat all bananas or not. Okay. So let's say for some particular value mid, you want to check whether Coco, if she has mid banana per hour speed, can eat all the bananas or not. Just think about it. There will be two outcomes of this question, either yes or no. That yes, she is able to eat all the bananas with mid banana per hour speed, or she is not able to eat all bananas with mid banana per hour speed. Now just think about it. If she is not able to eat all the bananas is in mid banana per hour speed, do you think she will be able to eat it in less than mid banana per hour speed? For example, if Coco is not able to eat all the bananas with 10 banana per hour speed, then do you think Coco will be able to eat all bananas in 8 banana per hour speed? No. Think about it. If you can't reach from one place to another place if by going 10 km per hour, you will definitely won't be able to reach that place in 5 km per hour. So you can say that less than mid values are useless. Can I say that? Here less than mid values are useless because if you can't eat in mid speed, you will not be able to eat in less than mid number of speed. So we only go to greater than mid speed, right? But just think about it. If she can eat it in mid number of, or I would say mid banana per hour speed, then maybe mid is our answer, or we can find better value less than mid. Can I say that? Just think about it. If from one place to another place you want to go and you are able to reach in, if your speed is 100 km per hour, you are able to reach that place. So we can say that yes, in 100 km per hour you can reach, and definitely in more than 100 you will also be able to reach. Just think about it. If from Delhi to Gurgaon you want to go and your speed of the car is 100 km per hour and you are able to reach in the desired amount of time, then you will definitely be able to reach if your speed is even higher, right? So going to greater than mid doesn't make sense. 100 km per hour can be your answer, but maybe you can find something even lesser than 100 km per hour. Maybe you are able to reach in less than 100 km per hour also. That is something that we are chasing. And same thing here. If Coco is able to eat all the bananas in mid banana per hour speed, then greater than mid also she will be able to eat. That means we need to find something lesser than mid because we want to minimize this value, that in what minimum speed she can actually eat the bananas. And don't you think this is going to lay down the foundation of binary search for us? In binary search, what we will be able to do, we will be able to divide our search space into two halves. With the mid value, we will judge, can Coco eat bananas with mid per hour speed or not? If not, then we will try to increase the speed. If yes, then we will try to decrease the speed. Now the only question remains is what should be the search space? What should be the search space? Now, what is the minimum speed that Coco can get? Minimum speed of Coco can be 1 banana per hour, right? Minimum speed of Coco will be 1 banana per hour. And what will be the maximum speed? Just think about it. Maximum speed can be only max of piles. Why? Just think about it. According to the question, let's say if she has 11 banana per hour speed, right? Can you see remaining piles has less than 11 bananas? Remaining piles has less than 11 bananas. So she will be able to eat all of them and will not eat anything more than that. Okay. And will not eat anything more than that. So the maximum speed that she can attain logically is maximum of the given piles, because any speed more than that is overkill. Just think about it. If her speed is 13 banana per hour, this speed is not required because you do not have at least 13 bananas in any piles. Can I say that? If her speed is 18 banana per hour, this is not required because there is no 18 bananas per hour in any pile. So the maximum speed logically that she should attain is 11 banana per hour, because at least in 1 hour you will be able to complete one pile. What is your goal? Your goal is to finish all the piles. What is the constraint? In 1 hour, doesn't matter what your speed is, you can only consider one pile. So why you want to have a speed more than the maximum number of bananas in any pile? Because let's say if your speed is 13, your speed is a waste, because you don't even have at least 13 bananas in a pile to eat in an hour, right? So the maximum that you can eat is max of pile. So I believe that will be your maximum value. And this can be your low value, this can be your high value. And based on this, actually, you can actually bring up your solution. How you can bring up your solution? You will calculate a value mid. You need to decide whether you can actually eat all the bananas at mid banana per hour speed or not. Okay. Now, how will you check that? If let's say your speed is mid, if your speed is mid, okay. Now, so now mid represents mid banana per hour speed that we are assuming, and we want to check whether we can eat the bananas in mid banana per hour speed or not within h hours. So what you will do? Let's say the value of mid is something m. What you will do is you will go to each pile. You will go to each pile and divide it by m. What is pile at I by m? It is number of hours required to finish ith pile. To finish ith pile. Can I say that? Just think about it. If your banana eating speed is 2 banana per hour and the pile has 8 bananas, then how many hours you need to complete this pile? You need 4 hours, because every hour you can eat 2 bananas. There are total 8 bananas. So in total you have 4 hours in which you can finish the pile, right? So if I divide piles at I by m, you will be able to get the number of hours to finish the ith pile. Number of hours to finish the ith pile. Okay. And just think about it. Now let's say your banana eating speed is 2. You have 7 bananas in the pile. If you do 7 by 2, what you will get? You will get 3. But do you need 3 hours to eat the 7 bananas? No. You need 4 hours. How? 2 plus 2 plus 2 plus 1. Can I say that? Can I say that? You need 4 hours to eat 7 bananas if your banana per hour speed is 2. Can I say that? So for this, technically, you need to take a seal value. Seal value means if let's say you have 3.2, the seal value of 3.2 is 4. If you have a value 3, the seal value is 3. Make sense? So you need to take a seal value of this. And you calculate seal value for every individual and then sum it up. Think about it. 3, 6, 7, 11. 3, 6, 7, 11. Okay. Low is equals to 1. High is equals to 11. What is the midpoint? Midpoint is 6. Now you are assuming that your banana eating speed is 6 banana per hour. Okay. How many bananas required to eat 3 bananas? Sorry, how many hours required to eat 3 bananas? Seal of 3 by 6. That is 1. How many hours required to eat 6 bananas? Seal of 6 by 6. That is also 1. Right? How many hours required to eat 7 bananas? Seal of 7 by 6. That is 2. How many hours required to eat 11 bananas? Seal of 11 by 6. That is also 2. So what is the total number of hours that you need? 2 plus 2, 4, plus 1, 5, plus 1, 6. If your speed is 6 banana per hour, then in 6 hours you can eat all of these bananas. And what is your time limit? 8 hours. That means this speed is good enough. Maybe this is our answer, or maybe we can reduce it. Maybe we can find even lesser speed. So we'll say low is equals to 1, high is equals to 5. Let's calculate mid again. Mid is 5 plus 1 by 2, 3. So now the speed is 3 banana per hour. Now the speed is 3 banana per hour. Okay. If the speed is 3 banana per hour, this will take 1 hour. This will take 2 hours. This will take 3 hours. This will take 3 hours. And this is going to take 4 hours. Right? This is going to take 4 hours. So what is the total time? 4, 5, 6, 7, 8, 9, 10. If your speed is 3 banana per hour, you need 10 hours to eat all of these bananas. That is too much. Our limit is 8. So you cannot do it in 3. You will not be able to do it in less than 3. So what you will do? Low is equals to 4. High is equals to 5. Can I say that? and so on and so on. You keep on improving the solution, and that's how you can actually solve this question, right? Now let's do one thing. Let's try to code this solution, and after looking at the code, we will be able to very easily visualize the time complexity of the solution as well. Now let's start implementing our solution. So first things first, what we are going to do, we are going to define the lower limit as 1. We are going to define the higher limit as maximum of all the piles. So if you have an array in JavaScript, you can calculate math.max as dot 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 piles. So what is this syntax? Okay. So you must be already aware about spread operator, right? So if let's say you have a array piles is equals to 1, 2, 3, 4, 2, 3, 5, 4. Okay. And you do this. Can you see you are getting 5? How is that? Because spread operator is destructuring or unpacking your array. And if it is unpacking your array, it is equivalent of saying math.max of 1, 2, 3, 5, 4. You can see, oh sorry. You can see you're getting an answer 5, right? So unpacking an array is making your command equivalent to this. And if you have multiple elements, math.max gives you the maximum out of it. Okay. This is going to take order of n time, FYI. Math.max takes order of n time to get maximum from n elements. And then what we are going to do, we are going to have, let's say, let answer. That is how much minimum speed you need to actually get your value. Okay. Let's say we'll start answer as 1, and we'll say while low is less than or equal to high. We'll say let mid is equals to low plus math.floor of high minus low by 2. Okay, cool. Now we are going to check. Let's say I'll write a function. Can eat bananas in mid speed. Okay, we are going to write a function can eat all bananas in mid speed. Okay, so for this I'll pass piles, I'll pass h, and I'll pass mid. Okay, so what this function will do, this function will check that whether Coco can eat all the bananas in mid banana per hour speed or not within h hours. How do you check that? I'll say let total hours by Coco is equals to 0. I'll say for let I equals to 0, I less than piles dot size or piles dot length, I plus plus. I'll go to each and every individual pile, and I'll say total hours taken by Coco to finish a pile is going to be math dot ceil of piles at I by mid. Can I say that? This is total time to finish ith pile. And what you are going to return? We are going to return if total hours by Coco is less than or equal to h or not. That total hours taken by Coco is less than or equal to the guard limit or not. If it is, then you can eat all the bananas in mid per banana per hour speed. If it is not, then you cannot eat all the bananas within h hours with mid banana per speed. So mid banana per hour speed. So we'll say if Coco can eat all bananas in mid speed, so I'll pass piles, I'll pass h, I'll pass mid. If yes, then answer is equals to mid, because this can be a potential answer, or we can find something lesser than mid to the left of mid. Else, if you cannot eat, you will not be able to eat it in less than mid time. So you need to increase your speed to mid plus 1. And at last you can return answer. That's it. This looks good to me. If I copy this, paste it here, run the code, you can see this looks good. Submit, and here you go. As simple as that. That's how you can actually solve the problem of Coco eating bananas. So this is the implementation for the solution of Coco eating bananas in Java. You can see what I'm doing is I'm having a variable low is equals to 1, and I'm having a variable high which will be eventually equal to the maximum of all of the elements in the pile. You can see maximum of all of the elements in the pile. How do you get that? This is also an order of n loop. You can see this is also an order of n loop with which I'm going to go to every element and get the maximum out of it. Okay, and then you say while low is less than equal to high, you calculate the mid, and then you call the function can eat all bananas in mid speed. So what is the role of this function? This function tells us that whether Coco can eat all the bananas in the all of the piles with mid banana per hour speed or not within h hours. So how do you calculate it? I have a variable total hours taken by Coco. This variable will hold how many hours Coco has taken. And then I go to each pile and I calculate this value. You can just directly calculate it like this. Pile set I by mid, and you can calculate math.ceil of it. Okay. Math.ceil of pile set I by mid. Okay. You don't need this parenthesis. Okay. So what is this function going to do? This function is going to calculate ceil value of pile set I by mid, because let's say if you have the banana eating per hour speed as 3 and pile set I is equals to 7, then you need how many hours? You need actually 3 hours. If you directly do 7 by 3, it will give you 2, but you need 3 hours. 3 hours for first 3 bananas, 1 hour for first 3 bananas, 1 hour for second 3 bananas, and 1 more hour for the last banana. That's why we are calculating ceil value. And I'm adding it in total hours by Coco because we are able to get individual hours for every pile. Now the total time taken by Coco, if it is less than equal to h or not, we are returning here. And if it is, then we get mid as the potential answer and we do high is equals to mid minus 1. Else, if we are not able to eat all the bananas with mid banana per hour speed, you will not be able to eat it in less than mid banana per hour speed. So I want to increase the speed. You can see we are increasing the speed. Hence we go low is equals to mid plus 1. Here we are decreasing the speed. Right? That's how you can actually solve the question in Java as well. Right? If you try to submit this question. Run code. 1 second. High is equals to mid minus 1. Low plus high minus low by 2. Let's start with 1. And this is piles at I by mid. Oh, my bad. Okay. Now in Java, if you do piles at I by mid, this will already give you a non-decimal value, right? This will already give you a non-decimal value here. Can I say that? Right? Because if let's say you have 7, you do 7 by 3, it is automatically going to give you 2. So what you have to do is, to get it in a decimal value, you need to convert your piles at I to double. Okay? You need to convert piles at I to double. If you run the code now, you can see it works, and you can see submitted properly. And what is the time complexity? What is the time complexity of the solution? Can you see there is an order of n loop to get the maximum? Okay, so let's write the complexity. Okay, n loop for getting the maximum. Then can you see this is a while loop? While loop of binary search. While loop of binary search goes on in log of search space time, right? What is the search space? Let's see. The search space is from 1 to max of the piles. Can I say that? This is the search space, right? So what is the binary search going to? Log of maximum of piles. Can I say that? But in each binary search iteration, you have a function call. In each binary search iteration, you have a function call. This function call is iterating over the whole array. So what is the time complexity of this function? Time complexity of this function is order of n. So in every binary search call, in every call, you are having a order of n loop as well. So you can see n plus n log of max of piles. What is order of n plus n log of max of piles? It is n log of max of piles. This is the time complexity for the solution. A lot of people think that the time complexity is n log n. That's a wrong answer. Why? Because binary search is not going for log n. Binary search is going from 1 to max of piles. So the search space size is max of piles. That is, this will become log of max of piles. So you can say, we can write here n plus n log of max of piles. Here we go. And this will be equivalent to order of n log of max of piles. that will be the time complexity of the corresponding solution. So I hope this overall algorithm of cocoa eating bananas is clear to everyone. And if you carefully see, the array that was given to us was piles, but we are not applying binary search on the piles array. Instead, we are applying binary search on the possible probable speed, because speed was the answer that we wanted to get. We are applying binary search on the speed, and you can see array doesn't represent speed. Speed is the answer that we want to get. Hence, this binary search is being applied on answer, and you can see it's a straightforward question of binary search on answer, right? That's the beauty here. So this is a new question coming from lead code, problem number 2300, successful pairs of spells and potions. Relatively newer question on lead code, 2400 plus upwards. You can see previously asked in Goldman Sachs. What the question says is that you are given two positive integers arrays. You are given two positive integer arrays, spells and potions. Okay, so you have two arrays, spells and potions, of length n and m respectively. So spells arrays of length n, potions arrays of length m, where spells at I represent the strength of the ith spell and potions at j represents strength of the jth potion. Okay, so if you have seen Harry Potter and everything, then there are spells and potions, right? Potions are like some kind of chemicals which has some magical powers, and spell is something kind of like a, like let's say set of magical words that you say and like something happens, right? You can consider an integer success. A spell and potion pair is considered successful if the product of their strength is at least success. Okay, so what they are saying is that if you consider some number success, then a spell and a potion pair, you can form a pair between spell and potion, and their pair is going to be considered successful if the product of their strength, that means the strength of the spell you considered multiplied by the strength of the potion you considered, is at least success. That means greater than or equal to the success integer that you took. Return an integer array pairs of length n where pairs at I is return an integer pairs of length n where pairs at I is the number of potions that will form a successful pair with the ith spell. Okay, so for example, this spell is 5. Okay, so this spell 5, right? This spell 5, and you can see there is a success number 7. You can see there is a success number given as 7. This spell 5 can form a pair with all of these potions. Can I say that? It can form a pair with all of these potions. Yes or no? So you can see there are 4 potions with which the first spell can form a pair, and hence the 0th index is 4. Now for the second spell, there is no potion with which the pair can be greater than the success value. So 0 for 1. For this particular spell, there are 3 potions in fact, for which if you will form a pair, it will have a success value greater than 7. So you can see 3 is the answer, right? You can see 3 is the answer here. So this is what you are expected to do. You need to actually figure out for each spell how many potions are there. Such that the overall pair product is greater than or equal to the success value. I hope the problem statement is making sense to everyone. Now, in order to understand this question, you can see in the question you have been given a spells array which is of length n, a piles array of, potions array of length m. Okay, and there is a success value given, integer value success given. You have to find for each spell how many potions are there such that such that product of spell and potion is greater than equal to success. Okay, this is what you have to find. For example, you need to find for each spell how many potions are there such that if you product them, the value will be greater than or equal to 7. So let's see. For this potion, which is 5, for this potion, which is 5, sorry, for this spell having a value 5, how many potions are there such that the product is going to be greater than equal to 7? Okay. Is 5 into 1 greater than equal to 7? No. Is 5 into 2 greater than equal to 7? Yes. Is 5 into 3 greater than equal to 7? Yes. 5 into 4 greater than equal to 7? Yes. 5 into 5 greater than equal to 7? Yes. So you can see for 5, there were 4 potions. There were 4 potions, right? That is eventually giving you the product greater than or equal to 7. And FYI, there is no such information that potions is a sorted array or not, or a spell is a sorted array or not. Until or unless we have been given that information, we should not assume it. It's a matter of fact that the test case looks sorted. Okay. Now let's do the same thing for 1. Is 1 into 1 greater than 7? Greater than equal to 7? No. Is 1 into 2 greater than equal to 7? No. 1 into 3 greater than equal to 7? No. 1 into 4? No. 1 into 5? No. There is no value with which we get the product with 1 gives a value greater than or equal to 7. So for 1, the answer is 0. For 3, is 3 into 1 greater than equal to 7? No. Is 3 into 2? No. Is 3 into 3 greater than equal to 7? Yes. 3 into 4 greater than equal to 7? Yes. 3 into 5 greater than equal to 7? Yes. So for 3, there are 3 potions such that the product with this particular spell is greater than or equal to 7. That's how you are expected to actually solve the question. Now, how can we actually solve this question? A pretty plain brute force of this question, if I think about a brute force solution, would be to form all possible pairs, of spells and potions. Okay, just try to figure out all possible pairs. Now, if you want to figure out all possible pairs, then what you are going to do? You are going to take one element of this spell and pair it up with every element here, right? Okay, cool. So the brute force will be to form all possible pairs of spells and potions. Okay, now what you will do is you will take a spell and pair it up with every potion here. Then you take another spell, pair it up with every potion here, and so on. How many spells are there? N. How many potions are there? M. The time complexity of this solution will be what? Order of nm. Can I say that? And how the code will look like? For I equals to 0, I less than n, I plus plus. For j equals to 0, j less than m, j plus plus. Okay. If spells at I into potions of j is greater than or equal to success. Okay. Based on this, you are going to actually put your logic. And you can see it's a nested loop directly having a complexity of order of nm. But if you carefully see the constraints, n is 10 raised to the power 5, m is 10 raised to the power 5. Order of nm will be 10 raised to the power 10. This is going to give you TLE. Now, how can we optimize? Optimization can be really easy. Let's think about it. You have a spells array, which is 513. And you have a potions array, 1, 2, 3, 4, 5. And you have a success value 7. Now just think about it. Is 5 into 1 greater than equal to success? No. Is 5 into 2 greater than or equal to success? Yes. 10 is greater than or equal to 7. Now for a moment, just think about it. If this potions array would have been sorted, let's say in the given example also it is sorted, but let's say we will manually sort the potions array in case we are given an unsorted situation. We are going to manually sort this array. Now just think about it. If you have a sorted situation and you realize 5 into 1 is not greater than equal to 7, but 5 into 2 is greater than equal to 7, and you know all the values to the right of 2 are greater than 2, then can I say all of these values can form a pair with this spell of value 5? Can I say that? Think about it. If 5 into 2 is greater than equal to 7 and everything to the right of 2 is greater than 2, so 5 can form a pair with everything from 2 to the right of 2. And let's say this is 0, 1, 2, 3, 4. How can we get the value? We can say n minus I, right? For example, this value is I. Okay. Length of the portions array is m. So it will be m minus I. M is what? 5. 5 minus 1 is what? 4. Can you see? 5 can pair up with 4 elements here. Yes or no? Right? Okay. Then you can see we have manually sorted this array. It is not already sorted. We have to manually sort it. Okay. Now for 1. 1 cannot find a value with 1, 2, 3, 4, 5. Any product for 1 is not going to work. So you can see the answer for 1 is going to be 0. This is 4. For 3, is 3 into 1 greater than equal to 7? No. Is 3 into 2 greater than equal to 7? No. Is 3 into 3 greater than equal to 7? Yes. Yes. That means everything from 3 to the right of 3 is going to be part of answer of 3. Now, don't you think? Let's say x is spells of I. X is spells of I. Right? You want to get a y such that x into y is greater than or equal to 7. Yes or no? So, don't you think lower bound can actually help you here? That is, you are able to find the first y. You are able to find the first y such that x into y is greater than or equal to 7. Think about it. Right? For example, the success value would have been 9. Then the first y for which 3 into y is greater than or equal to 9 is what? This 3. Because 3 into 3 is 9, 3 into 4 is 12, 3 into 5 is 15. So you want to find the first y for which x into y is greater than or equal to 7. And whenever you want to find the first value greater than or equal to something, lower bound can actually help us. So you can say you want x into y to be greater than or equal to success. Yes or no? You want to find x into y greater than or equal to your success value, right? If you want x into y to be greater than or equal to success, then you want y to be greater than or equal to success by x, right? You want y to be greater than or equal to success by x. So can I say I need to find the first value greater than or equal to success by x? And if you want to get a first value greater than or equal to something, you can take a ceil value of it, right? For example, let's say x is equals to 5. That means this portion we are picking. We want to find the first y for which we have the value 7 by 5. Okay, what is 7 by 5? 7 by 5 is going to be 1 point something. So what you should pick? Should you pick 1? No. You should pick floor of this value. So you want to find the first value of y greater than equal to 2. What is the first value of y greater than equal to 2? Index 1. Right? Then, let's say for 3. 3 will be 7 by 3, which is 2 point something. So if you take a ceil value here, it is going to be what? Greater than equal to 3. So now inside this array, you need to find the first value greater than or equal to 3. And hence you have a value greater than or equal to 3. So can I say for each element of this spells array, you can apply a lower bound on ceil of success by spells at I. Can I say that? For each spells at I, you can actually get a lower bound on this particular function inside this array. And whatever will be the index, from that index to the right side of it, everything will be the part of answer for spells at I. So how do you get? If you get a lower bound as let's say this value, then your answer is going to be m minus lower bound. Can I say that? And what will be the time complexity? You need to sort this array. So m log m to sort the array. Then you go to every element of this array. So there are total n elements. And you apply a binary search on this array, which is of length m. So you can say plus n log m. Can I say that? So if I write it properly, this is going to be order of m log m plus n log m. Can I say that? As simple as that, right? So a simple application of binary search can actually help you this question, help you solve this particular question, right? Now, interestingly, an easier way, or I would say one more way to actually solve this question can be using 2 pointers. How about, and 2 pointer, which was kind of like the similar technique that of with binary, merge sort. How about you sort this array as well? You sort this array as well, and you sort this array as well. Let's say you sort both of the arrays. If you sort both of the arrays, what is the time complexity? N log n plus m log m. Okay, this is n log n plus m log m, right? Sort this array, sort this array. And now just think about it. If you keep a pointer I here and you keep a pointer j here and you have a success value, let's say 7. Okay. Can you see 1 into 1? Is 1 into 1 greater than or equal to 7? Is 1 into 1 greater than or equal to 7? No. That means this particular one cannot form a pair with this one. This particular one cannot form a pair with this one to get the success value as 7 or greater than or equal to 7. Can I say that? Can I say that? Now, if that is the case, then what we have to figure out is that if this one cannot form a pair with this one, right? Maybe we can move j ahead, right? Maybe we can actually move this j ahead. Now, what will be the problem of moving j ahead? The problem of moving j ahead will be this one cannot form a pair with 2 also, right? This one cannot form a pair with 2 also. You will move j ahead again. But the problem is this 2 could have been paired with 5. Yes or no? This 2 could have been paired with 5. Yes or no? But if you will keep on incrementing j, if you just directly keep on incrementing j, then technically you're going to miss some probable solutions. Can I say that? You're going to actually miss something that could have been your answer. Yes or no? Right? You're going to miss that. Okay. How about you change your strategy a bit? How about you change your strategy a bit? Because here we are not able to decide whether we should move I ahead or we should move j ahead. Right? We are not able to decide that. Okay. In that case, how about we put a j here? Now just think about it. Is 1 into 5 going to give you any answer? No. If 1 into 5 cannot give you an answer, we are definitely sure less than 5 also will not give you any answer. 1 into less than of 5 will not also give you any answer. That means we need to, this particular value, spell set I is too less. We need to increase it. Right? Spells of I is too less. Right? Probably it would be relatively beneficial for us if we can move it. Can I say that? If we can move it ahead. Okay, cool. Now, can 3 into 5 be greater than or equal to 7? Yes. If 3 into 5 is greater than or equal to 7, then can I say everything to the right of 3 multiplied with 5 will also be greater than or equal to 7? Yes or no? Think about it. If 3 into 5 is greater than or equal to 7, everything to the right of 3 is greater than or equal to 3. So all of these values can be part of your answer. Yes or no? Right? Okay. Then you move j here. 3 into 4 is also greater than equal to 7. So everything to the right of 3 into 4 will be greater than equal to 7. You will add up all of them as well. Then 3 into 3 is greater than or equal to 7. So everything to the right of 3 will also be part of our answer. Is 3 into 2 greater than or equal to 7? No. So what I will do is I'll move I ahead. And now, is 5 into 2 greater than or equal to 7? Yes. Now from everything to the right of 5 is going to be part of our answer. So this can be an intuition using which you can apply two-pointer algorithm. You can apply two-pointer algorithm in order to form your answer. The only tight, I would say, situation you will land up into is to form your answer, because you have to form an answer for every spell at I. You need to figure out what could have been the number of portions that can give you a product greater than equal to 7. Now, because you have sorted the spells array, managing this can be slightly hard. Because you have sorted the array, you have lost the original order. So what you have to do? You have to remember the original order. Right? You have to remember the original order. In order to remember the original order, what you can do is, you have 5, 1, 3. You can make it 5, 0, 1, 1, 3, 2. That is value, index. And then you can sort it. 1, 1, 3, 2, 5, 0. And then you can actually sort it. And now, because you have access to the index which it was present at, you can maybe formulate your solution. So this is the intuition that you have to go with, that you start one pointer from the start of your spells array. You start another pointer with the end of the portions array, because in that way we are able to eliminate things, right? If we keep both of them on the start, we were not able to eliminate properly. But if we keep one on start, one on end, we are able to eliminate. And hence you can actually solve this question with two pointer. What will the complexity? N log n plus m log n plus n plus m, which is eventually going to be what? N log n plus m log n. Okay, so the complexity difference between both of the solutions is not too much. You can see here we had m log m plus n log m, right? Here we have m log n plus n log n. So only a factor of log n and log m is changing. So the overall time complexity is not going to change too much. And the binary search solution is relatively easier to think as well. But using two pointers also, you can actually solve this particular question. So I would highly recommend you guys to actually try to code both of the solutions, because me giving you code for every question is not going to help you in actually improving your coding ability. Rather than, you should try to actually solve this question with both of the approaches and see whether you are able to implement it or not. But I believe the overall solution to the problem is clear to everyone.